Swayam Prabha. Digital India. Educated India.
For this DC motor example, we are simply verifying that we have the conditions that are needed. First is that you have G, add f G and add f square G to be linearly independent, which turned out to be a little bit complicated. I will really ask you to try to verify this numerically, yeah. And then the second condition that we needed to verify was that the distribution formed out of G and add f G is in fact involutive, yeah, and that is pretty straightforward, turned out to be 0 0 0. So yeah, you have involutivity. Now we have by Frobenius theorem that this is in fact completely integrable, right. So therefore we have some output beta for which you have d beta multiplied by this terms of the distribution to be 0, okay. This is supposed to give you a partial differential equation. So I am going to expand this. What is G? It is I believe some 1 over Ls. And what is F? Add f G is this guy. Minus KLR R, KLR x3 and KJ x2. So this is 0, okay. So how do you find beta? Just write out the partial differential equations, okay. Let's see, what am I going to get? The first one is going to give me 1 over Ls del beta del x1 is 0, correct, right. This means what? What does this mean when you are trying to solve? Huh? Absolutely, implies beta equal to, in a very very bad notation, okay. Yeah, you should not write this, like, I mean, in a paper and all. In an exam paper it's fine, not in an article, yeah. But anyway, I am just saying beta is independent of x1, okay. What do I get from the second and third now? So you see that del b del x1 is already 0, right. So when I expand this one, I do not have to worry about this term, right. So I am going to simply write what? Minus k LR x3 del beta del x2 plus k j x2 del beta del x3 equal to 0, okay. So this is whatever, the k goes away, right. So I have some condition, right. How do I go forward now? You can guess, I guess. You can guess, yeah. What do you think? What do you think I should have beta? I will make this bigger if you do not see it well enough. What do you think you can get beta from here? See, it is very symmetric, right. There is x3 partial with respect to x2, x2 partial with respect to x3, okay. So to me it seems like there should be, x2 square plus x3 square, something like x2 square plus x3 square, yeah, because if I have x2 square, it becomes twice x2, this gives me x2 x3, and if I have x3 square, I get twice x3, I get x2 x3 again, these will cancel out, modulo some constants, right. Yeah, makes sense. Yeah, that's how I am guessing. Yeah, it's a trick, that's all. I am not doing anything magical here. Yeah, but you can solve any way you want, I guess. Yeah, I don't know again what is an obvious way to solve otherwise. Yeah, typically how you do solve PDEs is you assume it to be some that the two variables appear independently and things like that. There are some methods of solving PDEs. Okay, only in some cases you can analytically solve them. Yeah, but here I'll guess. So what is this, by the way? What is the scaling on x2 square and x3 square, you think? Can somebody tell me? Huh? LR x2 square plus j x3 square. Perfect, this will work. Why? Because it will give me, you can put a half if you want, but nobody cares. This will give me, the first term will give me LR x2, twice LR x2, so LR goes away. So this becomes x2 x3. This will give me jx3, 2jx3, so jj goes away, so x2 x3 again, so that becomes 0. That's a fair choice. Okay. So again, what did we end up doing? What is this beta? What was this beta? What was all this work for? Output. This is the output with respect to which the system is feedback linearizable. Now go back to what we had done. We had taken the system, fine, the friction was missing, no problem. I mean, there is this friction term that is missing from here, that I think has zero impact on anything. Yeah, this friction term is missing in the third dynamics, not here, no problem. But the output was pre-specified to some x3. Alright. Now what we are saying is that we are not going to pre-specify the output, we are going to try, we are not given an output, we are going to try to find the best output under which I get complete feedback linearizability. Okay, and that is this guy, LR x2 square plus jx3 square. Okay, and now that we have this output, why don't we try? Okay, try. I am going to say hx is LR x2 square plus jx3 square. Okay, what about h dot? Let me put a half if you don't mind. Yeah, I'll put a half. What about h dot? This is LR x2 dot plus j x3 dot. Notice that x2 dot and x3 dot don't contain the control. Okay, right. So this is going to give me some big mess, I am quite sure. Yeah, I am not even going to write it, sorry. I am not going to write it. Yeah, but I am going to compute h double dot. Yeah, this is LR x2 dot squared plus LR x2 double dot plus j x3 dot squared plus j x3 double dot. Yeah, just product rule used. Yeah, I don't want to write this mess, so I am avoiding writing it. Yeah. Now what do I know? I know that x2 dot square and x3 dot square are not bringing the control, right? Because x2 dot is this, x3 dot is this, does not have the control in it. But when I take the double derivative of x2 and in fact the double derivative of x3, I have to take derivatives of these guys, right? And here I have x1 dot appearing, here I will have x1 dot appearing. Okay, and that will give me the control. Okay, so what did I end up finding? That control appears. Okay, so what is it? Relative degree is what? Did I do this correct, by the way? Should the control be appearing here or in the third derivative? No, this is fine. Yeah. Sorry, I got all my coordinates. Yeah. I got all my coordinates, right? Or should I have, no, wait, I should be very careful. Did I get all my coordinates? What would be my coordinates in this case? They will be h, h dot and h dot. No, a control should not appear here either. No. Will the control appear here? Oof. This competition is so painful that I am not very keen on doing it. What is the control term? Can anybody compute it? Here and here? Can somebody tell me what is the control term? Forget every other term. What will be this term? What will the control term coming from this? LR x2, and in x2 double dot I have this guy, right? I'll have, so I'm going to write it as minus k ls LR x1 dot x3. Yeah, that is the term that is containing the control, is going to contain the control. Similarly, if I look at this guy, this is j x3, x3 double dot will be k ls over j x1 dot x2. Okay. Yeah, this x1 dot is going to bring the control. So I am just writing the terms in the control. My feeling is these two terms are cancelling, aren't they? These two terms cancel out, isn't it? Yes, minus k ls x1 dot x2 x3 k ls x1 dot x2 x3. These terms cancel out, right? Okay, that's the right thing to happen. Okay, now not going to write it, but h third derivative has control. Okay, it looked like this second derivative contains the control, but those terms will cancel each other out. So control doesn't appear, it can't, because I need 3 coordinates, right? I started with a 3-dimensional system. So my coordinates are now these 3, h, h dot and h double dot. Yeah, unfortunately, as you can see, very ugly looking. Yeah, well, nothing much you can do. Yeah, doesn't look very nice, but nothing much you can do. If you folks are enthused about it, we can try the other example also. Do you want to try the other example, or do you want to do it yourself? Why don't you do it yourself then? We'll make it an exercise. Yeah, I mean, we'll try. Actually, we don't know. So that was the other system. Which was, what was the other system we were looking at? We had this other example, right? This guy. This is even worse. No, we are not trying this. You can see that the g is not even a constant. No, maybe something else. Yeah. So I mean, see, fortunately or unfortunately, you can do, analytically you can work this out for very specific examples only. Yeah, but you can also see that you are, you are sort of coming up with some rather unusual transformations, okay, which you would never have guessed otherwise. Without looking at the structural details, you will never have guessed that this sort of an output would give you complete feedback linearization, right? We did work with some other, y equal to x3 and something arbitrary, right? Yeah, you would never have guessed that you would get feedback linearization, but yeah, with this very crazy looking coordinates, yeah, you will get a linear system in the end. Yeah, and this is not, like I said, this is not linearization or approximation of any kind. This is actually, the system is linear in these coordinates. Yeah, it's almost like, I think a lot of people say that if you squint your eye carefully enough, every nonlinear system is linear. Yeah, so if you look at it very carefully, every nonlinear system is linear. It's like, you know, so that's basically the idea here. Yeah. So a lot of them do have this condition satisfied. As you can see, it's not easy to verify. Yeah. Some of these I would still recommend that you verify numerically. Yeah. But for systems where you can do this analytically, you have a pretty powerful result. All right. A lot of times it's not a scale issue or anything. It's not like it's like n becomes large, there is a computational issue. It's not a computational issue. It's just that, for example, if you have 1,000 of the same kind of dynamical systems, and you can sort of by some suitable transformation you can make each of these dynamical system appear linear, then you have now 1,000 linear systems that you are working with. Yeah. So it's not going to affect you in terms of scale. Yeah. If you have some, you know, robot dynamic, like a mobile robot dynamics, which you can feedback linearize, yeah, then you can say a lot of things, right? Even if you have 1,000 such mobile robots, you can still control them with easier control loss, seemingly easier loss. Yeah. Of course, this nonlinear transformation will sort of play a big role, but the good thing is you have it's just a transformation now. It's just going from one function forward and one function backward. Yeah. Everything can be transformed like that. So yeah, I mean, there is a little bit of a pinch of salt associated with it, and this is also, I believe, yeah, there is a little bit more on, okay, I mean, there is just a little bit more on zero dynamics and so on. If you notice in the last slide of this, what I have done is I have looked at the rigid body dynamics, yeah, and I mean, although I have written it as an exercise, it's almost like I have done a little bit of the work myself. You can, or probably the entire bit of work, or actually at least a little bit of work I have done myself. So please take a look at this exercise. Yeah, there. This is the rigid body dynamics again. Yeah, in terms of some parameterization, you've already seen the rigid body dynamics. It's part of the current assignment also, and this is in some parameterization. Don't worry about what this rho is, but what I've asked you to do is to see if it's, you know, full state feedback linearizable and find the change of coordinates, yeah, which is this lambda. Yeah. So that's what I've sort of asked you to do, and I've actually checked a little bit of the, you know, involutivity and things like that. I don't know if I actually found the coordinates. Doesn't look like it as of yet. So yeah, you can probably give that a shot. Yeah. Basically, the idea is to find an output for which you have feedback, full state feedback linearization. Yeah. Actually, I think I have this. So I would encourage you to look at this, although it's like a solved exercise. Yeah. But I would encourage you to look at this. That basically it's. I have not used the integrability condition here because life becomes very hard with that condition. I have simply guessed that y equal to rho. If I take my output as rho itself, that's going to give me complete feedback linearization, because the second derivative will contain the control. Yeah. So I have sort of guessed at it again instead of actually going by the integrability condition that you have. Yeah. But this also works. So there is a lot of literature in spacecraft community where they use you know, this instead of using the rotation and the angular velocity as variables, they take the rotation and its second derivative and its first derivative as the variables. Yeah. Because in those variables you can claim some kind of linear system. Yeah. Though this is little bit more complicated than that. Yeah. Anyway, maybe we'll give you some simulations based on this. All right.